I'm here presenting with Ben, and I'm going to kind of set some context, and then he's going to give more details. But we wanted to touch upon a few topics on this journey towards programmability. And the thing is that when we think in terms of how to jumpstart a community and how to kind of change the industry, there's always like multiple approaches. Like one is top-down, kind of like defining a framework and kind of like defining how everybody or all the components are going to play within this framework. The other is more bottoms up and essentially describing some tools that they are useful by themselves and then having a vision on how those tools come together. And the point that we want to discuss today is that regardless of if we take a top-down or a bottoms-up approach to this community of kind of bringing programmability into data path and infrastructure transformation, we have to think in terms of composability. And we are going to emphasize this topic again and again, because as we think in terms of how to create an ecosystem of tools and components, we have to be able to create additive value to what everybody does. And we have to define abstractions and interfaces for this composability to work and lead into a flourishing community. So with this, let me start. So the first topic I'm going to mention is that networking is many things, right? And if you think from the distinction between network in the endpoints versus network in the physical network or the infrastructure components of the network, to the OSI model in terms of having 7 layers and certain layers kind of being considered transport or network versus certain layers being endpoint, or some of the control plane data plane separation. The thing is that the network has always been programmed. The question is, how can we program it even more? How can we drive programmability and innovation in all the components of the network? But just to emphasize that networking, programmability, and the evolution of networking is something intertwined within the community, and that we have to continue and flourish beyond the current level of programmability. Now, if you think like that, we always thought about this desire of wanting programmability in the data path, right? But traditionally, we had this notion of what function should go there. And we tend to think the ones that are slow, or the ones that are not well defined, or the ones that are in innovation state because we don't know yet how to properly hardwareize them in a very stable way. But the industry has transformed a lot in the last few years, and essentially programmability has become something that went from an exception because of the performance or cost nature of the components that we were using underneath to almost like mainstream. And nowadays we have almost like lots of technologies from MPUs to multi-cores to DPUs and so on, IPUs, that allows us to think programmability as the next wave to drive innovation. But at the same time, we have to think that there's been situations in terms of performance, cost, latency, that we have thought that having a hardwareized version was the way to go. And you always think that on a hardwareized form, things are more stable. On a programmable wall, things can be more dynamic. And this has implications in terms of who programs the network and why, and how does you bring stability and ownership and so on. So always think not only from the programmability aspects and why do you do programmability, but the fact that on operational environments that programmability has to be factored correctly. And if you look at the economics of these programmability aspects, the thing is that it's becoming more and more beneficial towards the programmable model, because basically the new components that we have in terms of programmability, they have a cost structure that sometimes outperforms some of the cost of developing ASICs. Now, if we take it to a more philosophical approach, it's like, what were we doing before having programmability, and how were we coping as an industry, right? And before programmability, we had to essentially agree ahead of time to what we wanted to implement. And that was through standard bodies, and then drive implementations and drive adoption. And that had kind of a long adoption cycle from an innovation point of view. Once we move to a programmable model, now what happens is that essentially instead of going through this definition phase, we can immediately jump into the implementation phase. And now once we have those implementations, we have to focus on evangelizing one specific implementation and why is it good for the industry, and then lead to an adoption cycle. And if you think we've switched some components, like the implementation and the ability to drive new technologies is much faster today. But if you think in terms of adoption time, when you look what it takes to transform connectivity, infrastructure, storage, and so on, we're still dealing with some long innovation cycles. But there is a fundamental difference in terms of how this innovation is accomplished. Like on the first model, we had a very well understood roadmap and what's coming in the future, but only a few companies or a few players could drive that innovation. Now we have shifted into a model that with programmability, essentially there is an explosion of innovation. That at the same time creates some confusion because now you don't know what's the technology to bet. But if you think from an industry point of view, even if the adoption cycles may be similar in both models, what we have brought is an accelerated innovation in the space of software programming infrastructure and the innovation associated to that. So from a benefit to the industry point of view, I think the explosion we've seen in the last years is a testament of this value of programmability. Now, from a technology point of view, what happened is that we were almost like evolving the network in cycles of performance. Like around 8 years, we would have a 10x performance factor, like 10 megabits to 100 megabits to 1 gigabit to 10 gigabit, and then to 40 gigabit or 50 or 100 and so on. But from a features point of view, we always inserted another generation in between or within a cycle. Now, what was happening is that from a CPU or programmability point of view, every time we have a jump of 10x performance, the CPU or the programmability aspect was increasing more linearly. And that created kind of this notion that programmability was a wave that was coming and going depending on where we're in the cycle based on the complexities of getting the right substrate from a performance point of view. But I just wanted to note that in reality, from a networking point of view, it's not just programmability, it's the memory management. And the first time that I saw like huge excitement in the network industry from a programmability point of view was with the appearance of the Pentium Pro that had a 1 megabyte cache. And at that time, that was like a lot of memory. And it was the first time that people started thinking, well, we could create a router with a CPU because now we can put the routing tables and the fibs and so on and the ribs into the cache in a way that all the memory access that we have to do essentially will be within the reach of forwarding packets. So I always think that programmability is not just programmability, there's memory access and so on that has to be part of this transformation that we do. Now, what we have to do when we approach network programmability is that we always have the two sides of the coin that I was mentioning before, the endpoint and the infrastructure. Now, we may have to take different approaches to scaling those two endpoints. If you think from a scaling point of view, we always have two models like the scale up and the scale out. And if you think from a network point of view, we have to do something similar. Like in the endpoints, we follow in terms of scale out. Like how do we bring networking capabilities into the endpoints, into the hypervisors, into the network stacks that run applications in a way that we have this linear scale. But all those aggregate into the physical network. And this is where we have to do scale up solutions. And this is where the programmable switches come handy. But essentially now the tools that we may have to use to program the switch and the tools we may have to have at the edge, they are potentially different. In one, sometimes becomes highly specialized. In the other becomes more at the realms of software development in the endpoints, which tend to be more flexible. And this is just to make the point that when we talk about network and network programmability, it's a broad topic. And depending on where you approach it, if it's from the endpoint point of view or from the framework of the infrastructure point of view, you may reach to different tools with similar fundamental principles about how do we bring innovation and programmability into the infrastructure. Now, back to this programmability for who, right? Who creates those components that we want from a network point of view? And we have these two communities that care about the network, the endpoint and the core network. And now underneath we have all these substrates from CPUs to DPUs, IPUs, MPUs, multi-cores, programmable switches, and so on. And the idea is that how do we create a set of compilers, tools, and abstractions that we can essentially create an ecosystem that is portable. how do we do in a way that when we bring an innovation that runs in a DPU, how it goes into the switch or vice versa? Or what do we do when we have an endpoint doing some network virtualization layer that can be ported into some hardware-based solution? And this is part of the theme that I've seen part of the previous discussions of how do we make sure that we don't focus on one specific architecture or one specific language, and we use sound concepts that we had in the industry in terms of abstractions to make sure that this community supports not only multiple devices underneath, but potentially multiple communities on top with different preferences in terms of languages. Now, going to end with this and pass it to Ben. The idea is programmability is a loaded question, right? And if you remember the early days of certain languages that you could create what we called spaghetti code and go to jams and things that were very difficult to maintain and troubleshoot. And then we learned how to bring modularity and abstractions and all the things that came through the industry. So here, what we want to do is now jump into some more details about how do we bring this composability aspect to make sure that as a community, we don't create a full stack or a full network solution that can only stand by itself and not leverage components, but how do we bring this level of modularity and that allows essentially communities to flourish. With this, I'll pass it to Ben.
Great, thank you, Pere. So yeah, I'm going to talk a little bit about ecosystems that have worked well. I think a lot of that is due to their communities, and one of the things that enables communities is modularity and standard interfaces and composability, like Pere said. We have some examples here of those sorts of things. Obviously, OpenVSwitch is the one that I'm most familiar with personally. But let's talk about some of the extra things beyond modularity that I think tend to make one of these communities or ecosystems succeed. Let's move on to the next slide. All right, so I think that from what I've seen, there's kind of a pattern if we're going to see one of these networking communities or ecosystems succeed. First of all, it helps a lot if it fills some niche that isn't well filled already. And in some cases, the hardest part of that is identifying that niche. And I think that the IPU and DPU is a pretty good example of that. It should be multiple purposes, or at least something that can be easily adapted for multiple purposes. The more people that you can draw in with their different use cases, the better the chance you have of building that community. It should be something that takes some difficult problems that maybe were difficult because the parts were hard to put together, and not necessarily because the problem is inherently hard. I actually think that NetFilter on the previous slide is an example of something where it did get a lot of engagement, and it still does, but for a lot of problems, it makes things harder than we had with OVS and OpenFlow, and therefore the things that tended to be hard and were easy with OVS moved over quickly. I think it also helps when you have something that can be useful for industry. I mean, that's what we're here for. But when you have something that attracts academics, so that people start playing with it, they start writing about it, they start spreading the word among students and faculty, that helps the sort of cross-pollination throughout the industry as well. It helps when you have a few identified people who everyone sees as the core maintainers, and those people actually pay attention and respond to other people in the community, both sort of curating and making their own improvements based on what they're hearing. And finally, my final point here is that that we always need a certain amount of patience. The anecdote that I've got here is I remember at an ONF event back around it must have been 2011, 2012 or so. Somebody who was well known at the time stood up and talked about their new project, and they threw up a timeline and said that by September there would be a support in the community. And it doesn't even matter what month this was at the time, because the point is that if you expect something to take off within the year that you launch it, you're probably fooling yourself. So let's take this and apply this to a couple of example ecosystems. If we could move on to the next slide. So EBPF is a great example, and this is just a drawing that I got off of the EBPF website. EBPF, I think it checks all these boxes, and it's seen amazing takeoff. EBPF can be used for so many things, and many of those are places where where you couldn't have done the things that people are doing with it without doing things that were very difficult, like modifying the kernel or writing your own kernel modules, which are both difficult and they're hard to integrate. It's something that I see coming up in all kinds of papers, and it's something that academics talk to me about all the time. It had the benefit of a couple of people who did and do a great job of advocating and building tools and maintaining it. And it might have seemed like it just appeared out of nowhere to some people, but it actually came up over years and years. And now the momentum there is huge. So let's move on and talk about the other one that I know much better than eBPF, which is OpenVSwitch. So when OpenVSwitch came along, there was the way that you would have done a lot of things that you do with it now would have been to write custom code or to try to program NetFilter, and using NetFilter to do the kinds of things you can do with OVS can be very tricky. Often it's possible, but it's very tricky. You can do a lot of things with OVS. And if you go to Google Scholar, you'll find that there are literally thousands of papers that use it or cite it. So we get the advantage of a lot of that cross-pollination. I talk to people in academia all the time, and I would personally like to claim that I was one of those responsive core maintainers for the first several years. I was out there reading every email on the mailing list, and often taking them and using them to improve it in different ways. And it certainly didn't come together all at once. Our first release was, I believe, 2009. But in those first 3 or 4 years, the percentage of patches actually coming from people outside of our core team was small. Now it's huge. So I'm going to now talk a little bit about one way that OpenVSwitch could have been made even more modular that sort of didn't come to pass. So on the right here, you see that this is the way that packets normally flow through OpenVSwitch. A packet comes in, it goes through some tables. If you're lucky, it hits a cache, and then it flows out whatever port or ports it should have, which works great when you can process something entirely inside OpenVSwitch. Which is probably the common case. Let's do the next animation step here. All right. So several years ago, we wrote a paper that was talking about another way that things could work to increase the modularity, where you actually have things flow from OpenVSwitch into a separate service element. we called this Softflow, and you can find the paper about Softflow if you go to Google Scholar. And the opportunity here was to better integrate external services into OpenVSwitch. And I'm just trying to make the point here that there are ways to make our systems that we already think of as modular even more so. And I want to make sure that that everyone keeps their eye open for that kind of opportunity. So this has been my discussion of how we can how we can sort of think about things as we're trying to build another community here. Some of the things that you might want to keep at top of mind. That's the end of my discussion. So Pere, do you want to close it up?
Yes. So basically, back to what Ben was saying, is that each community had its own reasons why success or adoption happened. And there's this aspect to make it useful to somebody and filling a space. As we get into these discussions between today and tomorrow, and we have these new data path components with IPUs and DPUs, let's remember what we said about the generality and the composability. And let's make sure that we introduce kind of like what's the goalpost in terms of the niche and the elements of value, and how do we make a community that from universities to industry to whatever, there's ways to collaborate and contribute independently and not find ways to kind of create framework versus framework and more like an ecosystem of components that we can all leverage.
Thank you. So we do have some questions. Pere, you talk about 4 to 7 years for adoption, even in an era of programmable networks, largely due to the evangelization and adoption steps of the cycle to achieve agreement and ubiquitous adoption. However, cloud operators don't care about ubiquitous adoption of a common architecture because they solve for their own specific use cases. Because of this, they tend to innovate much faster. Isn't there a scenario where enterprises start to innovate in this way using the programmable infrastructure at a much faster rate, breaking that assumption you made of 4 to 7 years?
Yes, and this is I was trying to answer in the chat, but the components and the innovation may come from anywhere, like back to the notion of breaking innovation from just a few and letting everybody innovate and consume that innovation. So in general, enterprises may have less expertise or skills in terms of developing network components from scratch. So the notion of programmability as a network engineer in an enterprise may be less common. But if communities like this one and the ones that Ben mentioned succeed, what happens is that the intellectual property that has been created is available to everybody. And now you may not need to program a new thing, you may need to consume and integrate this new thing into your workflows. And these enterprises are pretty good at. And now with the advent of DevSecOps and kind of like enterprise agility, this is more true than ever, where enterprises are adopting open source and platforms and networking technology, whatever it is, and incorporate it into providing security and connectivity into their applications. So I'm less, I don't think all the enterprises are going to jumpstart and program their networks the way the clouds do it, but the ability to consume the pieces of technology that we may create as communities like this one, they can consume it.
Thank you. That's the end of the questions we have for your section.